In the 42 programming course, I was tasked to make a simple fractal rendering program in the C programming language. We were, of course, allowed to use the math library for this. However, I completely oversaw this as I didn't properly read the subject. Then I taught myself the basics of imaginary numbers, complex numbers, and how these fractals are created. With this new forbidden knowledge, I will try to make new fractals no one has ever seen. First of all, what is an imaginary number and how does it lead to these beautiful visuals? Well, here's some history. First, only natural numbers existed, and even negative numbers and zero were denied. Then the government realized negative numbers were useful to track debt, and so they were included. Meanwhile, the ancient Egyptians already introduced the concept of rational numbers, so numbers that can be expressed as a ratio. Why did we add another set of numbers? Well, consider these basic arithmetic operations: plus, minus, times, division, and the square root. Adding two natural numbers can only give you another natural number. Naturals are complete under addition. With subtraction, we can create whole numbers or integers, as they're also called. This includes negative numbers. With division, we can create rational numbers, numbers that can be expressed as a ratio. The exception here is division by zero, which produces undefined results. With square roots, we can create irrational numbers. Square root of 2, for example, cannot be expressed as a ratio and has infinite, non-repeating, quasi-random digits behind the comma. The Greeks denied the existence of these numbers. Can you think of a new set of numbers now using what we have? Of course, square roots of negative numbers. No number times itself can yield a negative result. This is where imaginary numbers come in. Square root of -1 is defined as I, the basis of imaginary numbers. A complex number is basically a number with a real and an imaginary part, like 2 plus 3i. Now, no arithmetic operation, except division by zero, can have undefined results. We have answers to everything. Now, this kind of looks like a vector, doesn't it? Yes, representing complex numbers in a 2D plane, where the x-axis are the real numbers and the y-axis the imaginary part, is a common way to view complex numbers. What you'll notice is that multiplying any number by I will rotate it by 90 degrees. I times I is defined as -1. I times I times I is just this -1 times I, which yields -I. I times I times I times I is just -1 times -1 per definition, which is 1. And I to the power of 5 is just 1 times I, so I again. And then the cycle continues. What about adding and multiplying complex numbers? It works kind of like vector addition. Adding two numbers just means adding its two terms. Multiplying means using double distribution. Treat I like any unknown x. And then there's just one extra rule to follow. I to the power of 2 resolves to -1. Now we're ready to understand the mandelbrot set, which we're tasked to create. The mandelbrot set is a set, so a list of numbers, in our case complex numbers, for which a certain condition applies. These numbers are complex, and if we represent them in a 2D representation, we get this visual. What is this magical condition? It's surprisingly simple. A complex number c is part of the mandelbrot set if the function zn plus 1 equals z squared plus c does not diverge to infinity when iterated over and over. Z starting at 0. For some values of c it will run in a loop. For other values it will explode. The numbers that run in a loop are part of the set. The others that explode are not, and we will assign them a color, depending on how long they take until they explode. Let's get to work. We start by implementing a complex number struct, basic functions to add, square and multiply them, as we discussed earlier. We make a function, iterations mandel, that returns the amount of iterations needed for the value c to explode, or -1 if it does not explode within a range of iterations defined in the header. We create a square window with win size width and go through every pixel, translate it into the corresponding complex number, depending on zoom, and call the function. Now we can also experiment with color schemes to complete one of the bonus requirements, and arrow keys. For the last bonus point, we must implement one additional fractal, but we can do way better. What if we mess with the formula a little bit? In the Julia set, Z is now the parameter, or the pixel we're at, and C can be any value chosen by you. We implement a quick string to float to get user input, and see there, it works. We now have infinite freedom. It's starting to look like we're discovering these fractals, not making them, even though we made them. What about the ship set? It's exactly like the mandelbrot, but we take the absolute value of Z each turn. It looks very chaotic compared to the mandelbrot and Julia sets. Now, what else can we change in this formula? Z and C, that's it, right? But what about the exponent? Let's give the user control about if they want to square, cube, or raise Z to the 67. Please kill me. Now we have mandelbrot, multibrot, Julia, multi-Julia, ship, and multi-ship. Some of these I've never seen referenced online. And with 3 parameters, we can make multi-Julias that probably no one has ever created before. By now, I realized I can use the math library, but throughout the project, I realized it might be fun to see if I can finish it that way. And what I learned along the way was truly incredible. To finish it off, I wanted to make my own unique fractal. I called it the LENNERT fractal, and here's the formula. Yeah, it looks kinda mid, but it's unique and you've surely never seen it before. Guys, that's it. If you like the video, make sure to subscribe on the channel and like the video. Ah oui, ah oui.